Ask my instructor 3.6.65. The number of daylights at any point on Earth fluctuates throughout the year. In the northern hemisphere, the shortest day is on the winter solstice, and the longest day is on the summer solstice. At 40 degrees north latitude, the length of day is approximated by this daylight function, where D is measured in hours and T is measured in days. Approximately how much daylight in hours is there on April 14, which corresponds to T equals 103? So our job is to find the value of our function when T equals 103. To evaluate the function for T equals 103, I first simplify what's inside the cosine brackets. After I do that, I make sure that my calculator is in radians. And then I find the cosine of my angle and multiply it by -3 and add 13, and I get about 14.10 hours of daylight. Next, find the rate of change of the daylight function. To find d prime, the rate at which daylight changes in hours per day, we're going to use this chain rule for the cosine function. So I let u equal 2 pi times t plus 10 over 365. And I would like to find the derivative of cosine u with respect to t. Notice that u can be rewritten as a coefficient times t plus a constant. So when I go to take the derivative is just going to be that coefficient. Putting this together in the chain rule formula, I've got my u, I have my du dt, and so I know what my derivative is. Knowing the derivative of the cosine function, I'm now able to find the derivative of my daylight function. The derivative of 13 is just 0. And I already have the derivative of my cosine function. So this is my derivative function. My next job is to clean things up. And when I do that, I get this. Alright, so let's go back to the problem. This is my daylight function. It gives me the hours of daylight at the day t, where t runs from 0 to 365. And this is my rate of change. It tells me how fast or slow daylight is changing. I'd like to find the rate at which the daylight function changes. I'd like to find the rate of change for April 14th. So my derivative function evaluated at 103, I'm going to have to clean up what's inside my sine function. After I do that, I make sure that my calculator is in radians, and then I go ahead and plug it all in. And I get about 0.048 hours per day. To change this to minutes per day, I multiply by 60 minutes per hour. And so on April 14th, daylight is increasing. I know it's increasing because I got a positive value. Daylight is increasing about 2.9 minutes per day. Next, I'd like to graph the rate of change. Now, I'm not going to use a graphing calculator. It's not going to be available to me here on the computer. I'm going to use Wolfram Alpha. But before I do that, I just want to point out that this daylight function this rate of change of the daylight function has a period of 365 and an amplitude of 6 pi over 365 hours per day, which I changed to minutes per day by multiplying by 60. Now lastly, I can see that the graph should be shifted 10 days to the left. As I said, I don't have a calculator on my computer, so I'm just going to use Wolfram Alpha, which is a free website. You can see what I typed in. I told them to plot this function. I had to change it to horizontal notation, which is always a challenge. But they showed me how they interpreted what I typed in, which I really like. It's nice to see if I typed it in right. And this is the graph that they gave me. I'm going to have to interpret what this graph means. The graph on the horizontal, that's days, and on the vertical, that's my rate of change because I graphed the rate of change function. And at the beginning and end of the graph is January 1. And notice that period of 365 days. Remember, I had an amplitude of about 3.10 minutes increase per day, and that occurs when t equals 81, and the minimum occurs when t equals 264. The rate of change is 0 when t is 173, and then again when t equals 355. And I just put in here our April 14th. Remember, April 14th was about 103. And you can see that the light is still increasing, but it's not increasing as fast. It's only 2.9 minutes per day. All right, so that's everything for this problem. Have fun with it. It is a very interesting problem, and you can think about that as you watch the seasons change. Take care and have a great day.